This is lecture number 53. In this lecture, we are going to talk about critical performance limit in dynamic voltage scaling application and possible solutions. So, in this lecture, we will first talk about dynamic voltage scaling and applications, then device power supply, what are the transient type as well as the performance requirements, transient types and performance requirements, then what are the critical performance limits, and then power stage design conflict in case of dynamic voltage scaling application, and then what are the possible solution. I will discuss few solutions which we have worked on, but there are multiple solutions are also available and which will help to improve the transient response by means of circuit configurations. So, if we talk about dynamic voltage scaling in portable device, now the portable device is like common, right? It's like mobile phone, laptop, then there are many electronic gadgets, and particularly in post COVID scenario, these devices are like kind of is a common practice because we use more and more mobile phone, or other devices for video conferencing and so on. So, all these devices they operate in battery, like though in laptop we use adapter, but it is often expected because these devices are made for like to operate in battery. So, when you operate in battery, then there are many aspects in terms of, because each device has various computational requirements and there are various functionalities. So, based on that current voltage will differ, their based on their processing capability, their power supply requirement also will be different. But if we use such device, since there are many digital devices for processor, other application, where we need to provide a power supply VDD, that means for digital processor or power supply, this is VDD. This VDD, that means there is a supply for the digital processor. Whether should we use, because in digital supply we talk about any digital logic. If we consider we either talk about 0 or 1, logic 0 and logic 1, right. So, this corresponds to VDD and this is 0. So, this is our, we call it as a logic 1, right, and 0 we call logic 0. So, because of the voltage scaling, because the voltage is scaling down and down, so this VDD is also going down, because earlier days like it used to be close to 5 volt, now we are talking about 1.8 volt or even below, even around 1 volt. But this VDD also has some flexibility, even though we choose, let us say VDD, its nominal value, let us say we are talking about 1.2 volt or 1 let us say 1 volt is the nominal. So, let us say we are talking about 1 volt is the nominal, but this VDD we also have some flexibility within a noise margin. That means they can vary between 0.6 up to 1.8 volt. Why you do so? Because and within this range your logic will be decided like or treated as a logic 1. So, this variation in the voltage is provided to do something, and that we are going to discuss. So, if we use a fixed voltage, let us say 1 volt throughout, okay. So, that means it is a normalized frequency, then for a fixed voltage the power actually increases with the frequency, and we will discuss very shortly, the dynamic power is linearly proportional to frequency of operation, because a digital circuit we need to do frequently change the clock, right. At the clock edge they have to do certain computation. So, the normalized power linearly varies with the normalized frequency, whereas the power will vary in square of the VDD. So, if we reduce the voltage, then with respect to normalized frequency, then we can actually reduce the power, but reduction of the frequency also we need to check what will be the impact if we change the VDD. So, first of all, the dynamic power which I talk and which we are going to discuss, we want to reduce the dynamic power so that our battery life can be extended, energy saving will be more, battery life can be extended because we have battery and we want the battery to last for longer duration. But at the same time we do not want to compromise any performance, because these are all real time system. We cannot expect that suppose if you are doing some computation in real time, it has to do, otherwise the whole system will hang, right. So, that means there should not any compromisation in the processor performance requirement. At the same time we want to reduce the power. So, such dynamic voltage scaling processors are very much available with quantized voltage level, our defined like a Qualcomm processor, Intel, AMD. And there is another aspect which is like if you go for envelope tracking power amplifier, because now even if we want to talk about 5G communication, or even if you have for the communication device, or even if you want to do conversation like a communication. So, where that we have antenna in our mobile phone and the antenna is to communicate with the nearby tower, right. So, this kind of communication while talking, we need to adjust the supply of the power amplifier in such a way that, because if you use a fixed supply, then our battery will discharge very fast and the phone will get heated and it can burn also, but because of the losses. But if you want to reduce losses, then we need to change the supply of the power amplifier, which is actually supplied to the antenna, and in that process the DC-DC converter has to generate that variable supply voltage, and that require a very high bandwidth power supply. And all these phones uses this envelope tracking power supply like Apple iPhone, Samsung Galaxy, and there are many more. Now, this device power management in mobile processor, if you consider this Qualcomm Snapdragon processor, this is one of the example. We can take Intel processor and so on. We have many features because these processors are sitting in many of our mobile phone, and now the mobile phone you use for gaming, camera, right. Then now we are talking about AI processor, that means edge computation, because we need to reduce the computational power in we have many safety features, right. Even there can be many other devices, remote devices. Let us say if we use a smart camera, right, like a CCTV camera, smart camera. So, if we continuously take images, right, then we cannot manage with the memory, because that memory storage capacity requirement will be extremely large. But if we can store, if we find something going wrong, because the cameras are used to detect certain event, it may not be for the regular activity, or even there is no activity, why should you unnecessarily store, or why should you take the image, or why should you use the camera? The camera is on, but we are not taking the image, that means we are not processing the image. So, we want to first notice whether there is any activity, and if there is any activity, then also even if we just, because the activity can be normal regular activity, day to day activity, that also you should not store unnecessarily. There also we need a huge requirement of memory. But now using AI processor, we want to detect whether the activity is desirable or is something undesirable. So, this kind of algorithm is used to identify if something going wrong, and then we want to take the actual image with high resolution image, so that can be used as a proof. So, in such cases, these are all portable device, they are sitting somewhere else where there may not be any access to the power supply, because this may be a remote camera where it will operate by a battery, and we need to extend the battery life. So, as I said, there are multiple stages of camera. So, camera is just monitoring, but not storing, no processing. Then the power supply requirement may be very low. But suppose if there is some activity, but that activity the camera will slowly start activating its feature, processing feature, storing feature, but not to the full extent. As long as it identifies that something goes wrong, when it has to come to the full fledged, and then we require the maximum computation, and there the voltage requirement will be different. So, this performance requirement when we are talking about smart camera, when we are talking about smartphone, when we are talking about 5G communication, because even for communication also we may not need to use a high voltage or the same voltage level when there is no communication, or where there is only very like a little communication, like we are just surfing internet, then the data requirement is different, the speed requirement is different. But suppose we are watching a movie or we are playing online game, then the supply requirement will be different. So, all this requirement we should not use a fixed supply, because otherwise your whole power will be, battery will be discharged very within a short duration. So, the dynamic power, because all these processings are linked with the CMOS processor, where we use a VDD to supply the CMOS, and the VDD supply voltage decide the dynamic power. So, if we use a higher voltage, that means we need a high power. One of the examples, suppose all of us has laptop, right, and if you take most of the laptop, there are different battery features, like one of the feature is high performance mode, the other feature is balance mode, and the other feature is battery saving mode. What will happen if we operate all these feature without only when the laptop is running in battery, because we are not, suppose we are not using, we have not connected plug-in to the power supply, it is running in battery. In that case, if suppose we use the high performance mode, and suppose we are running, let us say MATLAB simulation, high extensive MATLAB simulation, then you will find the simulation is going fine, it is happening much faster. But suppose if suddenly change the power mode to the battery saving mode, you will find the MATLAB become very sluggish, it takes a lot of time, okay, and it can even hang. But if you use a balance mode, then it is a trade off, it will be lower performance than when it was the first case, the high performance mode, but it may be better than the battery saving mode. So, all these features nothing but changing this voltage and clock frequency of the processor. That means we have a processor where we have certain I would say certain voltage requirement and the clock requirement of the processor. Because of processor actual rating can be very high, we are talking about gigahertz processor, right, few gigahertz in the clock. VDD can vary, I told you that it has certain range, but we need not to operate the processor at the highest clock level, even you can operate at a very low clock frequency if the activity depending upon the task or the activities. So, if we can reduce the VDD, then we can reduce the dynamic power and we can save the battery life. Even we can reduce the clock frequency, we can save the battery life. But the penalty comes when you reduce the VDD of a digital clock. Let us say we are talking about a NOT gate, a simple NOT gate, where this NOT gate has a VDD, right, and since we are applying this signal, let us say Q, you will get invert Q, but this inversion will also come with a delay. That means it is about to get inverted, that we are going to see the Q bar, this is Q, but they are not exactly. So, it is, I can say it is not exactly Q bar, I would say it is something like Q1. So, you can see there is some delay, right, and this delay, propagation delay will be different or it will increase if we decrease the VDD of this NOT gate, because the propagation delay varies inversely proportional to the VDD. That means, in one hand we can reduce the power by reducing VDD, but on the other hand the delay increases such so that your computational the speed of computation, or basically the speed of computation task also reduces. So, that is why your MATLAB, when you are running a MATLAB with a lower voltage, then it will take more time. So, there is a trade off between power and speed, and that is what all about the dynamic voltage scaling. Okay? And in order to adjust this power dynamically, because we are talking about certain tasks which require certain voltage level and it also has certain deadline. So, we need to meet within the deadline and we can reduce the voltage as much as possible without missing the deadline. So, we need a dynamically adjusting or adjustable voltage for the processor, and that has, but we only have a one DC source which is a battery. So, that has to be done by a DC-DC converter or switch mode power converter. So, the objective of this converter to change this voltage in order to optimize the power consumption by this processor without sacrificing the performance or without missing the deadline. So, dynamic, and if you take the multi-core processor, because now most of the processors are multi-core because your computational requirement is increasing significantly, and at the same time our task has to be divided such that we can throughput can be very high. So, very high throughput, and that is what the multi-core processors are. But if for each core, if you use a single DC-DC supply, then if the task of all cores are different, then they may not, we may not be able to optimize the efficiency or the utilization of this core by using a same supply, because if you use the same supply to all the core, then we need to select the highest voltage so that none of the core miss the deadline. But maybe the core 2 may require a very lower voltage, so we are unnecessarily giving a higher voltage. So, the losses, the dynamic power losses in core 2 may be high. So, one supply for whole core may not be a good solution. So, can we then, should we use dedicated DC-DC power converter for each core? That would have been best, but that may not be practically recommended because that can huge expensive, it will be expensive. So many power converter because you have many cores like a 16 core, 32 core processor, but it depends. I mean, whether you really need, if the each core current requirement is high, it may happen that we need one converter for each core. Otherwise, you can make a cluster where the cores can be clubbed together, two cores can share one common supply and so on, and that can also be made. That means, we need to also think of dynamic voltage scaling for multi-core processor. Now, the next question, in dynamic voltage scaling, what exactly we do? So, as I said, the dynamic power is the square of the VDD and it is proportional to clock frequency. Let us assume that, and we already discussed about this trade off, delay and power. So, it is a trade off between power and speed. Imagine we have a task and the task can be executed, it has to be executed within the deadline. So, if we use VDD 1, the task can be finished in short time, but as I said, if you use smaller, I mean higher VDD, then the effective utilizations of the processor is low, and if such computation happen more frequently, then your VDD square increases. So, dynamic power increases. The another possibility, you reduce VDD to a lower level in such a way such that you do not miss the deadline. You finish the task and there you can save the dynamic power by reducing the voltage. But if you further reduce, then it will miss the deadline, then your whole purpose is lost because we can't miss the deadline, that is our limit. So, this technique this provides us, that means using a variable voltage VDD, we are talking about a variable VDD, enable us to optimize performance and efficiency. That means, we do not want to sacrifice the deadline. Definitely, if you reduce VDD, your performance will come down, but if it is within the deadline, that is fine, but we can increase the efficiency, energy efficiency, because it is the energy area under the curve, that means power into time is the energy, and each task requires certain energy. And if you can do that, we can save power so that your thermal overhead can be reduced, heat dissipation will be reduced, then board space and power can be reduced. So, it could save in many ways. Now, we want to find What are the existing methods? So, the simplest example is a synchronous buck converter, simple normal buck converter, where it is supplying to a processor, right. So, this is a very standard one. If the current requirement of this processor is low, let us say it is like 10 to 20 ampere kind of rating, a simple buck converter should be sufficient. But if the current rating of this increases or even beyond 10 ampere, in some cases, in some product, people go for two-phase converter, multi-phase converter. So, here I am just showing two-phase converter. But if the current goes above 20 ampere, then natural choice is you have to go multi-phase, because we need to divide the current among various phases, because we should not use high current for an inductor, because that will have lot of losses, and if you want to search for a higher current rating inductor, then the cost of the inductor will go up and also the losses will go up. So, it is better to divide the inductor so that they can share current. That is also another practice. The third one we will see the dedicated different converter, because suppose we need a VDD 1, suddenly we need another VDD like this. So, if we consider, this is my time and this is my VDD. Okay. So, this is my VDD 1, this is VDD 2 and so on. So, we want to change different VDD level. So, you have to do either by this converter, and we will show you there are challenges. We can also do by this converter, but we can also do by this converter when VDD 1 is sitting here and VDD 2 is sitting here, VDD 2. So, two dedicated DC-DC converter, and the processor can be connected to at a time one of them. So, you can change VDD 1 and this will be very fast, but this is a very more number of inductors are needed, more capacitor. So, it is a bulky solution, may not be a very practically recommended. But before I move forward, we need to first understand what are the different type of transient in dynamic voltage scaling, because as usual when a DC-DC converter is supplying a DC-DC converter is supplying to a processor load, that means you are a processor load, we have a supply here Vin. Then in case of dynamic voltage scaling, first of all, for any case the processor current will change, there will be frequent transient. Let us say there will be frequent transient, that this is related to load transient, because this transient happened due to the computational requirement that is going to change, and that is something it is common, very common. But in addition to that, in VDD we need to change VDD, change it or vary. Why? Because we discussed if we want to reduce the dynamic power, we need to change VDD. So, that means we can expect transient in I0, that is my load transient, we can expect the transient in reference voltage, that is for reference voltage transient, or their combination. So, if we take the time optimal recovery, because we discussed in the previous section, we want to achieve the fastest response, and which we can use a switching control scheme, and in fact we have discussed the large signal based controller tuning can be used to achieve this kind of response, and that will get the fastest response. We can also achieve that same tuning rule, but maybe a different gain parameter, the fastest response for the reference voltage change when it is changing from one voltage to the other voltage using fastest time. And the other possibility, you can have a combination of load and reference transient. So, all these three possibilities exist, and we want to now analyze what are the parameter and how are we going to design the power stage. So, the devious power supply requirement, we need a minimum settling time or basically minimum recovery time, and that is why we talk about time optimal control, time optimal recovery that will reduce, because the linear control cannot meet that, right. Then we also want to reduce the peak current, because if the peak current during the transient, if you go back to this, so the peak current generally we determine this current, this is my peak current, right. So with respect to the next operating point, what is my, or I will say not peak current, I think the overshoot, this is not the peak current, the peak current is absolutely this one, this is my peak current, okay, this is my peak current, and this particular part is my current overshoot. So I am concerned about the peak current, because this is there is a limit due to the inductor, because inductor cannot carry arbitrary current, and even if we talk about the BH characteristic of the inductor, so we should not go into the nonlinear region or the saturation region. So that also you have to check carefully. So the peak current, and if we can, that is for the inductor point of view, but in general if the peak current is high, then your energy overhead can increase, and that we will discuss. The device rating, that is the inductor rating as well as switch rating has to increase, and also there can be more thermal overhead can be increased. Reduce. So if we can reduce the peak current, then we can reduce both energy overhead, that means we can reduce the rating of the device, inductor size, the rating of the inductor, that coil or basically the gauge rating of the inductor, that can be reduced. Then thermal overhead can be reduced, heating effect, so you can save the space, board space. We have to reduce the voltage undershoot, because this is supplying to a digital processor where there will be a noise margin, so you cannot exceed the noise margin. So the logic level compatibility has to be met. And first we need to reduce the component count, and the control should be simple feedback control. And this part I think we have discussed, that if we use our large signal tuning using a simple current mode control, that is a very simple technique that is used in many commercial products. By setting this controller tuning, you can get the fastest response. So though digital control allow us to do very high performance control, but we want to make our control simple, because ultimately it will be translated into silicon area and the price. So the time optimal recovery, if we take a buck converter, then we are talking about the first is transient, and that we have discussed already. We already have identified what is my peak current, we have already identified what is my recovery time. So this time is my recovery time, TR, that we have already discussed, and then we have also discussed the voltage undershoot. All the expressions we have already discussed. Now what are the constraints on the peak current, recovery time and the voltage undershoot? So the peak current, you find it is basically delta I0, that means depends on the step size, and which is quite common, but it also depends on the square root of Vref by Vin. So that means if the input voltage increases, then your peak current decreases, because this is in the denominator. But if the input voltage decreases, then peak current increases. That means if you operate at a lower input voltage, then your peak current can significantly increase. But if you operate high input voltage, then there is a problem, because the duty ratio will be smaller, and we have found in the very first or second week that lower duty ratio will lead to higher losses, because the RMS current will increase, and also higher input voltage can affect the switching loss, it can increase the switching loss. So the losses in the converter will increase when we operate at a higher input voltage. So another thing, the input voltage in most of the cases is not in our hand, unless we use a two-stage architecture. So that means our peak current is limited by this. Recovery time, if we go to, it is high at high input voltage and large inductor. So recovery time, if you go, if the duty ratio decreases, then recovery time, actually it should be the other way around, recovery time high at higher input voltage or the lower duty ratio, no, high at, okay, so there is a typo, so high at lower input voltage or this can be larger inductor. If the inductor value is large, then recovery time also increases. So, that means the recovery time high at lower input voltage or larger inductor value. Then voltage understood high at smaller capacitor or larger inductor, because if you go back, voltage understood increases if you reduces the capacitor value or increases the inductor value. So, natural choice is that we should take the characteristic impedance. That is why in most of the power supply design, we take L by C to be very small. That means our inductor is small and capacitor is large. But how can we reduce voltage undershoot and current overshoot even for a given inductor capacitor value? Because we cannot increase the capacitor value significantly, because there is a penalty in the power density. We cannot decrease the inductor value significantly, because there is a penalty in terms of RMS current, right, the losses. So, can we increase without affecting the power stage, or can we achieve near ideal voltage regulator without very less output impedance and very low bandwidth, a very high bandwidth? High bandwidth. That means ideal, almost ideal output impedance and bandwidth. So, what is the ideal output impedance? That means we have learned the ideal output impedance should be very low, in fact negligibly low, and this should be very high, extremely high. It should be very high. Okay. Then we have to go, we need to make some circuit rearrangement, otherwise it is not possible. So, during the load step up transient, we need to provide an extra path, because what happened during the step up process, suppose if you take the dash line, your capacitor current sees, when there is a load step transient, the whole step size appear across the capacitor current, because your inductor cannot change immediately, because it has an inertia and it undergoes a load step transient of delta t, it has increased. So, this step size will appear in the capacitor current, and that is what we are getting. And it takes time that capacitor current to become positive, but till then your voltage will fall, and that is the problem of voltage undershoot. So, it is bound to happen. But what happens if we can anticipate by providing an external current? That means we are giving a current here from the source, that is my source current, in such a way, in case of perfect anticipation, in such a way that when there is a load step transient, the whole step size will appear and then it will slowly decrease. In such a way, the capacitor current becomes 0. That means we want this capacitor current to be 0 during the large recovery, so that the load step transient, whatever is happening, it will be anticipated by this external current, and since the inductor current is rising, so this has to fall, so that at some point inductor will take it up when it reaches to the next steady state point, and this current will slowly become 0. That means it starts decreasing and it becomes 0, and this is exactly what is happening. And if you can do that, then you will find the capacitor current remains 0. So, there is no change in the output voltage, almost negligible change. And if you can do that, then we can say the output voltage is not changing at all, or inductor is changing, but that it is not affecting the output impedance. So, since there is no variation in the output voltage, so we can assume that it has 0 output impedance as well as it has infinite bandwidth, because it is not changing at all. But this is a practical converter, this is achievable if we can anticipate by this current. But what is this circuit? What is this circuit? That itself is a question, because it is like a variable source and it is not so simple, and it will also come with a price, because we are adding extra component, so the price will go up. And so, what we did in this paper, we have used a resistive one like augmented path, and if we same thing can happen during step down, that means here we are providing this extra current through source to get something similar by using multiple resistance. Similarly, during step down transient, we can anticipate by excess charge in the capacitor has to be removed and that can be dissipated by the resistance. As it said that since it is a resistive component, so the power will be dissipated as a heat energy, and that is the fallacy. But there are many other technique where this can be replaced by another auxiliary inductor. So that means you can use another branch of converter like these small branches with auxiliary inductor, and that can be connected here. But this inductor can be very small. In fact, in many multi-phase solution, these auxiliary phases are used to boost the performance. It is kind of a booster operation where we can speed up the response by introducing an auxiliary phase where the slope is very fast. So, the current can be increased rapidly because the slope of the current depends on auxiliary phase. It is V in minus V0 by L A, where L A is very small. So, you can speed up by providing this excess current. So, ultimate objective get something similar. Ideally, if we can achieve zero capacitor current, but practically it is not possible. So, there are multiple circuit which can achieve which can offer some practical solution. So, one of them is a resistive one, but this will be lossy if the transient happen more and more frequently. So, this converter we want to get the phase plane behavior, because we have discussed if this is my one steady state operation and when there is a load step up transient it goes like this, then it hit and it come back to the next operating point and stays there. Okay. So, this is a first load step up transient. During step down it is again coming here, hitting and turning off, right. So, the turn off I would say this is turning on, this is turning on. So, different color, and this is the turning on path. So, here also if we can provide this auxiliary path from one point to the other point, it will simply go like this or it will simply come like this. So, there will be no overshoot undershoot, and this path can be discarded if we can make that ideal arrangement, there is no problem, but practically it is not possible. So, what we have to do? We have to find out solution. So, one of the way we told that we use a resistive network, okay, and this is the time optimal recovery of a conventional buck converter. So, this is like a conventional buck converter, or I will say a classical buck converter which is given where we are using a diode. So, we are using a diode based converter, and you see when there is a load step up transient, the inductor current is going from one point to the other point in time optimal recovery, there is no problem. And when it is coming from this point to this point, it is also kind of time optimal, but because this particular phase it is in DCM mode, discontinuous current, when the inductor current becomes 0, when IL is 0. So, as a result your capacitor is simply discharging across the load during this when IL equal to 0. And since the load current is low, the rate of discharge is very slow and it is taking lot of time, okay, and there is a huge overshoot, and this undershoot overshoot may not be acceptable in the future processor requirement, where we are talking about cloud computing. There can be hundreds of ampere load step, and such high load step can result into large overshoot undershoot, and that simply by power stage design and time optimal control it may not be enough. So, we need to think about some auxiliary circuit to cut down the transient. So, this is a time optimal recovery. Again, these results are taken from this paper which you have presented. Now, if we consider the auxiliary path, suppose during the step up transient again the load current increases here, but now we have enabled the auxiliary path, and auxiliary path we have used two resistance with switches, and during that time the capacitor current is supplied, or basically what it is happening, that means we have this IS current which is coming from the source through the resistive path and it is getting added. This is my inductor, this is my capacitor, and this is my load. Okay. So, this capacitor current, since this source current is directly providing to the load. This is my load, and inductor current is ramping up. So, the capacitor current changes negligibly, it remains nearly equal to 0. As a result, you can see there is insignificant change in the output voltage ripple, and this is AC coupled result because this is 0.2 volt per division, and the ripple band, this is almost negligible change, and we found that the deviation in the output voltage is constant within the ripple band. That means we have cut down the whole trajectory which was there. You can see that there was a such high overshoot, undershoot, and this is my ripple band, this is my ripple band. Okay. So, I want to cut down the transient, I want to keep my voltage and current within the ripple band, and I want to cut down this transient. Okay. So, this is possible by this augmented path, and there is no transient. Same thing. So, these results again are taken from this paper where we have presented for detail, and then there are subsequent methods are developed, but in this course we want to just emphasize some aspect which will motivate to think that how can you develop auxiliary circuit. If you take the step down transient, that is one of the problematic case, and if you go here you will find in the step down transient this undershoot of voltage undershoot was is AC couple around 0.2 volt, 0.2 volt per division, right, sorry 0.2 volt is the magnitude, 0.2 volt, and the current overshoot in this case also the current overshoot was how much, it is like a 1 ampere. So, it is roughly around close to 2 ampere, right. So, here in this case there is no current overshoot. So, no current overshoot, no current overshoot, and no voltage undershoot. Okay, so, it is almost like an ideal converter. Same thing happened for our step down, it is almost within the ripple band. So, that means it is possible to cut down the transient by means of circuit configuration where we need to change it. But this method that we have used, it is long back, it is a resistive method that can be lossy. If such transient come more frequently, then you may have losses in the converter, and those aspects are also discussed in this paper. But subsequently there are many methods are developed to cut down transient without penalizing too much of the efficiency. Okay. Now, the time optimal reference transient recovery. So, we talk about load transient recovery, now we are talking about reference transient recovery. In reference transient, we have a peak current, and here the voltage has to change from Vref to Vref plus delta Vref, and we have discussed the peak current, recovery time, these two are the parameter that we are going to discuss. And if you compare the time optimal parameter, if you take the load step transient, we saw the peak current is basically delta I0 d, where it was like a delta I0 into referent, that means ref by V in, right. And you saw at higher input voltage it was so low, but lower input voltage it was very high. But if you take the peak current for the reference transient, you see it is a function of capacitor, it is a function of inductor, it is a function of there should be delta D, actually delta D. So, this should be delta Vref, this should be delta Vref, sorry, delta Vref. So, this reference voltage. Okay. So, here this load step, that means what does it indicate reference transient? If my, for a given low reference step size, if my inductor decreases, then the peak current increases. If the capacitor increases, the peak current increases, and if you reduce capacitor, peak current can be reduced. If you increase the inductor, peak current can be decreased. But if you go to the recovery time for load step transient, you see the smaller inductor achieve faster recovery, that we have discussed. But of course, it has a penalty in terms of higher conduction loss, but that also you have to decide. So, in the power stage design, we generally tend to design a smaller inductor. But here also recovery time, using a smaller inductor, you can reduce the recovery time, but you see it increases the peak current. So, smaller inductor increases peak current for reference transient. Similarly, if we go to the voltage undershoot, generally for load transient we use a larger capacitor to reduce the undershoot, but this is something opposite requirement for reference transient, because a larger capacitor will increase the recovery time and larger capacitor will increase the peak current, because in reference transient we know that half C, what do you say, V1 square minus V2 square. That means, if you use a larger capacitor to change voltage from V1 to V2, you need more energy from the source. If the capacity increases, this energy requirement goes high. As a result, peak current increases and the recovery time increases. So, in load transient, for load transient, we generally need small inductor and large capacitor. But for reference transient, we need small cap. And we also need, the inductor choice is also conflicting, because if you take a large inductor, peak current will reduce, but your recovery time will increase. Okay, and the peak current will give you energy overhead, and the recovery time will give you time overhead. So, it is a conflict, right? Small capacitor is mandatory, but that is conflicting. And even if you take a large inductor, you can reduce the peak current, but you will end up with longer recovery time. So, there is a conflict in the power stage design when we want to simultaneously, we want to design the converter which has to cater the first recovery for load transient as well as the reference transient. So, the time optimal performance, if I show a result that is taken from this, and it is given in this paper, that if we want to change the voltage from 1.8 to 3.3 volt, you can see it takes a longer duration, right. So, it is taking almost 30 microsecond, and with a high peak current, the peak current is very high, this peak current is very high. So, this peak current is very high, this is my peak current, very high, around 12 ampere, and here the peak current is minus 10 ampere, so very high peak current. Okay. So, the regular converter, when like a normal buck converter which we have designed earlier using load transient for small l, large C, this is detrimental for reference transient, because we saw that there is a conflict. So, the design conflict for the inductor load step transient, we need a smaller inductor for faster recovery and lower voltage undershoot. For reference transient, smaller inductor reduces recovery time, but it significantly increases the peak current, that is what we saw. If we take the capacitor, that means this should be capacitor, if we take the capacitor, larger capacitor reduces the voltage undershoot during load transient. So, it is the good positive part for load transient, but it significantly increases both peak current and the recovery time for reference transient. So, the large cap, if you take large capacitor, and that makes the DVS power supply design, DVS power supply make design conflict. And because of this conflict, if we want to because if you go to various processor like Intel, Qualcomm, other processor, the reference voltage we have to change from one to the other. So, in practical reality, the kind of converter are used, it takes time to reach from one voltage to the other voltage. It may not be obvious or immediate, and that increases, and that transient time or basically recovery time give rise to, first of all, time overhead, underlocking. That means our required voltage is here, because this voltage can be, let us say, can be the voltage of the processor, or it can be voltage of a ring oscillator which generate the clock. But if it takes time, then you require more time before you actually start activating the ring oscillator locking, because in between the voltage is changing and you may not be able to correctly predict the actual frequency coming out of the ring oscillator because of this voltage transition. So, the underlocking time overhead is quite large, and it is mainly occupying the whole time is taken almost by the underlocking time. That means when it is voltage is transitioning. But if we talk about energy overhead, that means I told you, so there will be high peak current. During this time, your peak current will be significantly higher, right? Inductor peak current. So, it will undergo high energy overhead, and it is primarily because of the DC-DC converter. It almost close to 78% is occupied. And this voltage also, underlocking behavior of this voltage also create energy overhead, because this you are using excessive lower voltage. So, as if you cannot use the actual PLL before this, that means before this, as if you are using a earlier frequency but using extra voltage. So, the frequency deviation. So, we need to take care that PLL, how to this transient time, the voltage rising time will actually give an underlocking behavior where the voltage is not perfectly locked. So, it will give rise to energy overhead, and this is discussed in detail in this paper. So, one solution, how to cut down, because we found the problem load transient and reference transient has some conflict in the design. So, one of the solution, we take one inductor and two pre-charged capacitor, and at any point, suppose we want to change from one voltage to the other voltage, suppose you use this capacitor as your output cap, and let us say this is sitting at 1.8 volt, and let us say this is pre-charged to 1.2 volt. So, we can change between 1.8 and 1.2 very frequently. That means we can increase the number of capacitor if the more number of voltage levels are required, right. So, here it is showing the two capacitor case where you can change the voltage from V1 to V2. This parasitic capacitor is very small, very small, but this is your load. Generally, this is your processor load I0, and this will be connected either to this V1 terminal or to this V2 terminal at a time. Only one terminal should be used. So, you can change either 1.8 volt or 1.2 volt, and that will happen almost immediately. And if you require such more number of voltage level, so you can increase the number of capacitor, right. But there is a penalty, because more capacitor. So, if you need, let us say 100 number of such voltage level to optimize my DVS power consumption, then should I need 100 number of capacitor? No. So, we can use a voltage deterring technique. That means, if my required voltage in the dead line is my dotted line, right, then I can use a higher voltage to finish early, but that I said that it is not a good way. So, you will lose more power. Then I can take two different voltages. Suppose I have two voltages are available. So, one voltage is my V2, as I said, maybe at 1.8 volt, and other voltage is my V1. This is my V1, which is, let us say, 1.2 volt. So, my effective voltage requirement Vd, which is this, and this we have to finish within the deadline. So, if you use Vd, then our task will be finished within Td time, that is my deadline. But ultimately it is the energy. So, that means we are talking about the Vd in Td, this area under the curve has to be same. So, this Vd can be generated by alpha times V2 plus 1 minus alpha time V1, where alpha belongs to 0 to 1, and this alpha is a fraction of time when V2 is on, V1 is on. Okay, and that means it will be decided. So, suppose if my VD requirement is, let us say I need something 1.5 volt and my V2 is 1.58. So, what I am getting 1. So, if I put it here, 1.5 is equal to alpha into 1.8 plus 1 minus alpha into 1.2. If you solve it, then you can find out alpha. So, how long duration you can run? That means here only two capacitors that we have discussed. These two capacitors are enough, but we need to change it from 1.8 to 1.2 for alpha into t time, and which we call duty ratio, but we are not saying duty ratio because it is not operating at the switching frequency. So, it is the output frequency which has to be changed, and alpha into t times we will use for this terminal, and 1 minus alpha into t out we will use for this terminal. Okay, there is interchange, and this is some voltage design technique can be used. And since our technique support very fast transient response, because you see here we are using the same design criteria of a low transient response, smaller inductor, larger capacitor. So, we can change the voltage level from this to this almost immediately, whereas in a regular buck converter it requires large amount of time, and these results are taken in this paper, it is discussed. So, your time recovery is much larger, and here it is like almost instant. Secondly, you see the current overshoot is much higher. Here the current overshoot is almost cut down, there is no current overshoot. Now, in conventional converter, if we want to put a current limit, because there is a limit in the inductor, because we are using a peak current mode control, then naturally this recovery time increases, time overhead increases, the recovery time increases, and that is something not acceptable. And if the recovery time increases, then your processor power supply, that means you want, this is the ideal processor power supply requirement, but it is actually changing like very slowly from this part to this part. So, your uncertainty will increase further because it is taking longer duration to reach from one voltage to other voltage, but here you can make it almost immediately without any current overshoot. So, the voltage dithering technique that we have shown that if you change the voltage from 0.95 to 1.2, 1.35, 0.95, you can see there is no current overshoot undershoot in this method, and it can change immediately because we have taken 4 different, here 3 different voltage level we are switching, and in the first case we are switching between 2 voltage level, alpha time T out, this is this duration, I would say. Okay. So, here you can think of alpha time T out, and here you can think of 1 minus alpha time T out. So, this is used to achieve the desired voltage of 1.075. Okay. By changing this available voltage 0.95 and 1.25, we can achieve that. Another task we can achieve by using 1.35 and 0.95. Okay. So, you do not need too much of capacitor in the architecture, you can reduce it, and by that way we can achieve any voltage level using this voltage design technique, and there is no current overshoot. So, this reduce significantly. That means, so what is our ultimate requirement? We need certain VD, that is our desired voltage, but this can be achieved by alpha times 1 voltage plus 1 minus alpha time V2 voltage, and by means of voltage dithering. And we can execute the task, and this will be equivalent to our VD, the task can be executed. And since our technique actually cut down all the transient, it can reach immediately this voltage, we can change it. But still, you know, still we are using more number of capacitor, because even if we use 2 capacitor, more switches, more capacitor. So, this can be reduced significantly in the multi-phase, that multi-core processor, that because that can be challenging. In multi-core, if we want to optimize, you know, let us say cluster based approach and this cluster based approach. So, what should be the right strategy to do that? That is also another challenge, because the future is going, you know, it is already in multi-core. So, you can do DVS, but the technique that we have told, it should not be scaled directly for multi-phase, then you have too much of capacitor requirement. So, there are scope for optimization for multi-phase, and that will motivate to come up with new and new architecture, where we can reduce time and energy overhead. So, those are that are the objective for future, and in multi-core it is interesting to see how it happens. Okay. So, I am not going to discuss in this lecture, but we have developed this and we have filed a patent, but this technique, I mean, for multi-core there are several challenges, and future that can be a very good future research problem. So, in summary, we talked about dynamic voltage scaling and application, we talked about dynamic power supply, DVS power supply transient type, performance requirement, we talked about critical performance limit and power design, power stage design conflict, and then we also talked about some possible solution and circuit configuration for fast transient, but there are still scope for further optimization, and that actually kind of motivate us for future research. So, with this I want to finish it here. Thank you very much.